Hey everybody, I miss you guys. I'm glad that we can at least do lessons in this way. It's our first one since the spring break and the coronavirus outbreak. So we're picking up. Well, really, we left off at the end of the topic. Right now, we're picking up with something called duality. All right, and there's a dual for each LP that we've been working with. So that's kind of what we're going with today. Oh, that's kind of sloppy. Is we're going to start with finding the dual. Of an LP. Okay, that's what today's lesson is mostly focused on, is finding a dual. Then we'll do a little bit of exploring with the duals. So the first question is, what is a dual? What is a dual? And I'll kind of lay this out to you. It's kind of like the evil twin, or the opposite, kind of in most ways. There's literature defines a dual in this way. A dual is another LP in another space, another mathematical algebraic space, that is an equivalent, or has an equivalent solution. So they come to the same answer, but we'll talk about that later. I just want you to know that using duals, there's a lot of powerful solving ability whenever we have the possibility to use duals. There's a lot of theory behind this, and we'll touch on that throughout this and the next few lessons. So first, let's kind of learn to write a dual. Okay, I'm going to start with a kind of a baby example. So here's our LP. We'll call it the primal LP. Primal. That means it's not the dual, it's the first one, the primal. And let's say we're maximizing z equals, and we're going to do this all in matrix notation, sum cost dot product with the x's. Subject to, and then, the constraint matrix is a times x is less than or equal to b. And of course, all the x's are non-zero. Well, the dual to this, the dual LP, would look something like this. It would be a minimization. And instead of calling the objective function z, it would be w is what's used in most literatures. And then here's where the weirdness starts. It's almost like turning this problem on its side. So instead of the cost times the x, it's actually the right-hand side times, like I said, it's in a new algebraic space, so a new variable, a new vector of variables is needed. So we'll call those y's. So it's b dotted with y, subject to, and it's actually going to take the A matrix, the constraint matrix, and transpose it, multiply by y, and that's going to be greater than or equal to the cost. And we still want all these y's to be non-negative. So these are duals of each other. Actually, if you were to take the dual of this one, you would get back the primal. So the dual of a dual is just back to the primal problem. Okay? So they kind of look like perfect opposites, right? One's a maximization, one's a minimization. The costs are down here, the right-hand sides are up here, kind of switching spots. The A matrix will be transposed. Hopefully you know what transposed means. And we switch out the variables. And this is interesting. Since we're transposing A, the size will switch. So if A was like a 2 by 3, this one's going to be a 3 by 2. That's kind of interesting, because it might be easier or more difficult to solve depending on its size. Like, say you have lots of variables, so lots of extreme points to pivot to. But if you were to turn it on its side, it has less variables. Maybe that would be easier for you or your program to handle, or the other way around. Maybe you don't like a lot of constraints, so you take the dual of it, and you would have less constraints, just a lot of variables instead. So it's some people use this in creative ways. Okay, so I do want you to notice, like I said, the changes here, the changes that happened, changes that have occurred. We went from a max to a min. Our C and our B, our costs on our right-hand side, traded places. The constraints went from less than or equal to greater than or equal to constraints. I'll put CONST. The A matrix transposed. And still, kind of as a note, variables are still greater than or equal to 0. That didn't change. Okay? So you could try to remember this. One way to do this is to convert every matrix into this form. Does anybody remember what this form is called? This is, well, I'll write it on the next page. This form is actually called normal form. Normal form. That's when we have a max, and we have constraints less than or equal to b, and we have variables greater than or equal to 0. That's normal form. Okay. So some people, actually, I had a professor who who would change. There's a list of rules for when things are not in normal form of how to write the dual, and he said he hated memorizing those. He would just convert everything to a normal form and then write the dual of it. And that's perfectly fine. Let me give you an example. Let's go with a primal LP. Let's see. Let's go with max z equals, what should I do? 2x1 plus 3x2 subject 2. And let's see. Let's go with x1 plus 2x2 is less than or equal to 5. x1 minus 5. x2 is less than or equal to 1. 4x1 is less than or equal to 10. And all the x's, which is only 2, I won't be lazy. I'll actually write them both out, are greater than or equal to 0. So this actually is normal form. Can I write the dual? The dual LP. Let's see. Well, instead of a max, it'll be a minimization problem. Instead of z, we'll call it w, the objective function value. Now, instead of x's, I'm going to have y's, right? Here, the dimension of this problem is there are 2 x's and 1, 2, 3 constraints. So that means the dimension of this problem is going to have 3 variables and 2 constraints. And we use y's for those variables. And the multipliers, remember, it's going to be the right-hand side times those y's. So 5y1, y1 is going to be the piece representing constraint 1, plus 1y2, plus 10y3. Okay? Subject 2. And let's write out all the constraints now. What's going to happen here is this matrix will be transposed. So for instance, this first row will become the first column. Sorry, I said that backwards. The first column will become the first row. So we will have 1y1 plus 1y2 plus 4y3 is greater than or equal to, because that was the switch from less than or equal to constraints to greater to or equal to constraints. And then what was the c on the first column? The cost was 2, so greater than or equal to 2. That's a sloppy 2, but y'all all heard me say it. Y'all know what we wrote there. And if I keep this going, it'll be 2y1 minus 5y2, just reading down this row, the column right here, to make this new row. There's no y3, and it's going to be greater than or equal to 3. And I don't have any more room down here, but we also want the y's. I'll be lazy this time and do yi's. Greater than or equal to 0. Okay, so there, we constructed our first dual. How do you feel? That's nice, right? So this was beautiful because this was in normal form. Now, we have learned a few tricks. You can always convert to normal form. Like, for instance, if one of these are pointed the wrong way, couldn't I multiply both sides by -1? And that would flip the inequality. There's also a trick for if they're equal to, which I'll talk about later. It's basically the same trick that we do for when we have an unrestricted and signed variable, which you may want to pause and think about that. There will be some relationship with how we handled unrestricted and signed variables and how we handle equal signs in the constraints. Okay, so it's pretty simple for a max. For a normal a normal LP. Also, if this wasn't a max, I could turn this into a max problem, right? We've learned that as well. So let me give you a list of rules for when it's non-normal, okay? So for a non-normal, for non-normal. So when you don't have it in that beautiful thing, we'll go ahead and just assume we're talking about the primal being a max LP, but you could do this for a minimum as well. It doesn't really matter. So we'll call this side the primal side. And we're going to be switching to the dual. And let's see all the changes that happened. Okay? So obviously the first thing is if we're going from a max and we're writing the dual is going to have a min. Okay? Now, let's look at the constraints in the primal problem. The constraints in the primal problem are going to affect the variables in the dual. Okay, because everything's turning sideways, that should make sense. Because the constraints over here, if you think about this, the constraints in the primal are the right-hand sides, or kind of what we're thinking about, the b's, right? Well, those become the cost, which have more effect on the variables. Those are going to become the cost over here. Okay? So, let's see here. So if it is a less than or equal to constraint, we saw that in the normal form, that's just going to turn into the variables being greater than or equal to 0. If it is a greater than or equal to constraint, greater than or equal to b, that's going to lead to the variables actually being less than or equal to 0, negative, which we know how to fix that. It's okay. We can still solve and use a simplex because we've learned how to handle some of these things. And then if it's an equal sign in the constraint, that's going to lead to the variable being unrestricted in sign. Okay? So now we're going to do the same thing for variables and how they affect the constraints over here. Okay? So if a variable is less than or equal to 0, or greater than or equal to 0, or equal, or unrestricted, sorry, I got carried away, unrestricted, the constraint in the dual will be less than or equal to its right-hand side. If it's less than or equal to 0, the constraint will be less than or equal to this. And if it's unrestricted, the constraint will be an equal sign constraint. Okay? So some people memorize this whole entire giant chart. Some people just convert things to normal, because you can always use algebra and a little bit of intuition to convert to normal. And then just change, because it's easier to remember that little bit as opposed to all these things. But let me give you an example where I do both. Okay? Let me give an example where I do both of these. So, let's let this be our primal LP. So notice we're not really doing anything with them yet. We're just working on writing them, because that actually takes people a little bit of effort sometimes to come up with. Z equals 2x1 plus x2. And the constraints are going to be x1 plus x2 equals 2. 2x1 minus x2 is greater than or equal to 3. x1 minus x2 is less than or equal to 1. And let's go with x1 non-negative and x2 unrestricted in sign. So the question is, can I write the dual of this LP, the dual LP? And hopefully I can. So let's see, instead of a max, it'll be a min. Whoops. Get carried away there. W equals. So let's see, how many constraints do I have? 1, 2, 3. So how many variables will I have over here? 3. y1, y2, y3. And they're going to have multipliers of 2, 3, and 1. 2 plus 3y plus that. There. Subject to. So see, I only have only have two variables, so I only have two constraints over here. So the first one's going to be y1, 2y2 plus y3. So y1 plus 2y2 plus y3. And it's going to be greater than or equal to 2. Why is it greater than or equal to? Because the variable for the first variable, x1 variable, is greater than or equal to. So that means the constraint in the dual will be greater than or equal to. And it's going to be 2 because that's the cost. Okay. Now my next one's going to be y1 minus y2 minus y3. It's the easy part to write. And it will be equal to 1. Why is it equal to? Well, what's the second variable? It's unrestricted in sign. So that means the second constraint is going to be equal to, and it's relating to the 1 from that cost right there. Okay, awesome. Now I need to figure out how y1, y2, and y3 are going to be as far as negative, positive, non-negative, unrestricted, whatever. So the first variable over here relates to the first equation, the first constraint, and it is equal to, so that means the first variable will be unrestricted. Okay. The second constraint is greater than or equal to, which means the second variable will be less than or equal to 0. And finally, just like with the normal form, it's less than or equal to, which means our variable in the dual will be non-negative, greater than or equal to 2. So there we've done it, but that took a lot of thinking about all these different pieces, right? So just to reiterate that I can get the same thing, I could just convert this to normal form and then find the dual really easily. Now look, it's going to look a little bit different. Let me see if I can squeeze this on this page. Normal, so it's still going to be max z equals. Now, for it to be normal, I'm going to want both my variables, or all my variables, greater than or equal to 0, which I know how to fix that by doing that substitution for unrestricted in signs variables, right? So to get to normal, remember, we're going to let x2 prime minus x2 double prime equal x2. So that'll give us all of our things being greater than or equal to. So let's see if I could do this without too much stress all at once. There, I made the substitution there. We'll make the substitution all through here. Now, I'll go ahead and tell you, to fix an equal to problem, we can do the same thing. We can make it, think about this. To equal to, that would be the same thing as having two constraints that are identical. That one says you have to be less than or equal to 2, and one says that you have to be greater than or equal to 2. Well, the only way to meet both constraints would be to be equal to 2. So I can do a similar thing to fix this or equal to by breaking it into two constraints. Okay? And if we're calling them y1, we can call it y1 prime and y2 prime. Because over here, y1 prime and y1 double prime. Over here, y1's unrestricted. How would we fix it? We would break it into two different variables, just like we subbed over here. So you see the relationship between an equal to equation and an unrestricted variable. So now I'm going to want them both to be less than or equal to, right? So I'm going to need to multiply 1 through by -1. So let's see if I can do all of this at once to save on writing space. So x1 plus x2 prime minus x2 double prime is less than or equal to 2. Now I'm just going to take this and have less than or equal to, or greater than or equal to 2, but multiply through by -1, so it would flip to less than or equal to -2, and it would flip all these signs as well. So plus x2 double prime. There. I think I've done that without being too horribly confusing, right? Hopefully so. Hopefully that's not horrible. Okay. Now how can I switch this one to be less than or equal to? Multiplying through by a negative. So that'd be negative 2x1 plus x2. So plus x2 prime minus x2 double prime is less than or equal to -3. And this one's perfect. I just got to make the substitution here. x1 minus x2 prime plus x2 double prime is less than or equal to 1. And now all of these, x1, x2 prime, x2 double prime, are all positive. So this is normal form. So the dual, writing the dual, would be actually pretty simple now, as opposed to having to memorize all these random things. I'm fine if you do either, but this is easier memorization wise. You don't have to struggle as hard trying to memorize what you're going to get. See, so I got 4 constraints now. Fixing this equal sign did give me more constraints, whereas here I only had 2, not 4 constraints, 3 constraints, 3 variables. Fixing this unrestricted and sign, three variables are going to give me 3 constraints here. Sorry, I got carried away. So let's see. I'm going to have y1 prime, y1 double prime for this constraint. I'm going to call them both y1 just so I can relate them here. You could call it y1 and y2 if you wanted to, but it doesn't matter. Plus y3, let's say, or y3, y2, and then a y3. Sorry. So now, let's see, what are the variables going to be? The multipliers. 2, -2, -3, 1. So 2 minus 2 minus 3 plus 1. Subject to. Transpose this, and we'll get y1 prime minus y1 double prime minus 2y2 plus y3 is greater than or equal to 2, because remember, now they're all going to be greater than or equal to's. And what am I going to have? 2, 1, and -1. Because I made this normal, so writing the dual is actually really easy. So y1 prime minus y1 double prime plus y2 minus y3, and then finally -y1 prime plus y1 double prime minus y2 plus y3, and all the variables, I'm just going to lazily write it this way, yi's are all non-negative. So that, writing the duals this way. Writing the dual is easier, but it took a lot of work to fix this. But I haven't given you many problems this nasty. This is just showing you how tough it could be, where you have to see everything like unrestricted and signed variables and equal sign constraints and less than or equal to's and greater than or equal to's and all that nastiness. But that's how we would write the dual. Okay? So next, what I want to do is take a problem, an example. I've already worked it out, and I want to see if we can discover kind of the relationship between primal linear programming problems and duals. I want to look at the relationship between these two types of things. So there's a handout that I'm going to include in the email and post on Blackboard. Here it is. And it takes a primal and its dual. Notice it's in normal form, so it's not that nasty or hard to do this with. And it solves each of them. So if you look over at the primal side, it solves pretty easily. It's just a few pivots. Write it in a table. And just trust me on the pivots. Read it later when you have some time. Notice the cost of the objective function goes from 0 to 20 to 24. And there's no attractive. We're optimal. Just 2 pivots. And the optimal's 24. It increases at each pivot. That's how the linear programming works. The Simplex method improves at each pivot, unless there's degeneracy. Right? So let's look at the dual. So we've written the dual. Now, because of the dual being greater than or equal to constraints here, I need either 2-phase or big M, because I don't have that trivial starting solution. So I introduce 2 artificial variables. I update all the cost. Now I can do some pivots. In 2 pivots, you're out of the phase 1. I chose 2-phase because that's my favorite. You could do big M if you wanted to. So now I have phase 2, and I have a starting solution. But first I have to update the cost. That's on the next page. So I update the cost, and it's only 1 pivot away from being optimal. I have a pivot to make, one attractive variable, a pivot. So look at what the cost is. It's about, now this is a minimization problem. It's about 24 2/3. You pivot, and now we're at 24. So it minimized, it went down. Or optimal, there's nothing attractive. Notice that the objective function value picked up on the same solution as the other. See if I can find the other thing. 24 was the answer. The dual picked up on the same thing. Notice something else, though. The dual decreased at each point. Okay, so just a very interesting note that the optimal for the primal, Z, and the optimal for the dual, W, are equal when we're at optimality. Let me go ahead and tell you something strongly important, though. This really only works all the time for linear programming problems, which is another reason that linear programming is way better, or easier, or considered a done deal, way less confusing than nonlinear or integer problems. Okay, now I want to harp on this more next time, but there are a few reasons to want to be able to do duals, because sometimes either the primal or either the dual is a lot faster. One of them usually takes a lot less pivots. This one only took 2. This one took a lot of work. Sometimes it's not the primal that's easier. Sometimes it's the dual. So some people just use it to come up with an easier problem. Some people like to use other methods, and I'm going to teach you next time something called the dual simplex, which is really neat, and it helps when you have difficulty with feasibility, or infeasibility, I guess I should say. So for now, I just want you to be able to write a dual. Next time, I'll give you a few theorems relating the duals to each other. I do want to point out one more thing. Notice all these solutions increased up 20, 24. Well, if you count 0, 0, 20, 24, increased up to 24. And all of these, once you got out of the phase 1, went down to 24. So that's where they're operating in different spaces. And duals and primals are kind of interesting. So they're in different spaces, different constraints, different everything, but the dual is minimizing down to the optimal and in complete different spaces. This is a horrible drawing because they're not even on the same planes or anything. But the primal optimizes up to the same solution. So they will achieve that when they are equal, we know we are optimal with LPs, only with LPs. And that's actually some method people use to know when they have an optimal, is seeing if the dual and the primal are equal. There's a whole lot of powerful stuff here, which we'll talk about more next time. But because the dual always is minimizing down, you could use it to make an upper bound on a solution. And the primal, you can just hit a feasible solution and use it to make a lower bound. Then you know your answer somewhere in between them. They do this a lot with the airline trafficking problems because those, remember I told you, had a lot of degeneracy. And they could take millions of pivots before the airline scheduling, before you get to the optimal. So often they run their code for hours and then cut it off. They run a dual and they run a primal, and then they have an upper bound and a lower bound, and they know the optimal's somewhere in there, which makes them happy because they can achieve one of the, they can achieve a solution that's good enough. With real big world industry problems, it's not always easy to get the exact answer. But I'll leave you with that. That's enough to think about for today. And then next time we'll pick up with some really, really fascinating theorems from all of this stuff. All right, so y'all have an awesome day.